So I have to use the integral version of the center of mass formula, which says the integral dm times the x-coordinate of the center of mass is equal to the integral of each dm times its corresponding x-coordinate. So if this piece right here is dm, each dm has its own unique x-coordinate, and I'm taking the sum, the integral of each dm times its x-coordinate. But usually we don't write the integral that way. It's written the integral of x dm. Now, you might think you need parentheses like that, but those parentheses are understood, taking the sum of x times dm. Now, we don't want to integrate over dm's, so we're going to want to transform the dm into a dx. Each little piece of mass corresponds to a change in the length, dx. And in order to transform between dm and dx, we have to use the linear mass density. Now recall, linear mass density is equal to mass divided by length. And if it was constant all the way down the line, then the mass of the whole shebang rod would equal the constant value of lambda times L. But in this particular problem, lambda changes as you go further to the right. So we cannot say lambda times the whole length because lambda changes bit by bit as we go to the right. But what we can say is dm is equal to lambda times dl, because if dl is small enough, then the value of lambda is constant over that dl. And another way of writing dl is dx, so we could say dm is equal to lambda dx. And in this problem, lambda is equal to 2x, so dm is equal to 2x dx. So that's a way to transform this mass right here into this dx. So notice this left-hand side right there, the sum of all the dm's, that's the total mass right there. So what we get in front of this xcm, that's going to answer this first question right there. So this integral dm can be rewritten as the integral, but instead of dm, we know we could replace dm with 2x dx. Whoopsie. And then that's all going to be multiplied by the x-coordinate of the center of mass. And then that's going to equal the integral symbol, there it is right there, times this x right here. But then dm is going to be replaced by this phrase up here, 2x times dx. And these integrals, we want to go from x equals 0 all the way down to x equals 2 because we want to get the whole bar. So we're going to be adding up these dx's from 0 to 2. From 0 to 2. Now remember, the fundamental theorem of calculus says instead of actually adding up these products like this, we can take the antiderivative of what's sandwiched in between the integral sign and the dx sign. So if we take the antiderivative of that 2x, we would get x squared. And we're going to do that between 0 and 2. And then that gets times the x center of mass. And then over here, again, we're going to take the antiderivative of what's sandwiched in between the integral sign and the dx. And the antiderivative of x times 2 times x, well, that's 2x squared. So that's going to be x cubed times 2 over 3. Because if you took the derivative of that, you would get 2x squared, and that's what we had up here, 2x squared. And again, this has to be done between the boundaries of 0 and 2. Now, if I substitute in the 0 and the 2, I end up getting 2 squared minus 0 squared times x center of mass equals 2/3 times 2 cubed minus 2/3 times 0 cubed. And on the left-hand side, I get 4 times x center of mass equals, and on the right-hand side, I end up getting 2/3 times 8. Now, I want to remind you, this right here was this right here, which was the mass. So the mass of the bar was 4 kilograms. And now to get the second question, the center of mass, divide both sides by 4. The x-coordinate of the center of mass is going to end up being, divide that 4 under, I get 2/3 times 4, which is 8/3. And that ends up equaling, what's that going to be? 2.7 meters if you do it to 2 sig figs.